Okay, so this is lecture 1 for geology. So the very first chapter. The slides may not be as bright as I'd like them to be. I'm working on getting another projector so I can actually have a little more areas to play with as far as changing scales. But this seems to be the best design. This is the same slide presentation that is on canvas right now. So you can either look at it under the modules or in files. So I'll go through this. So geology is the study of the Earth. 4 major divisions of Earth science are geology, which is probably the most important one. It studies the lithosphere, which means the rock. Biology studies the biosphere. This is all the plants, the animals, the interactions. Hydrosphere, or hydrology, deals with atmospheric conditions, water, groundwater, travel time of water, surface water, streams, anything that has to do with water basically. And atmosphere is kind of a little mixture of hydrosphere and the atmosphere. But atmosphere deals a little more with weathering, weather patterns, storms, climates, and of course the atmospheric concentrations of greenhouse gases, studies things like climate change. So people who are into the atmospheric sciences are also climatologists. They're people who are looking at climate. So earth science is the study of the earth. So basically geology, this isn't earth science. It's probably the most important earth science of them all. And it deals with kind of every one of these interact to form geology, where geology has a direct impact certainly on everything. So a good example is what plants live where they live, and animals generally depends on geological conditions such as mountain ranges, the type of rock. As it turns out, in the Sonoran Desert there's going to be tall sword cacti, and they seem to like rocks that are igneous, especially rhyolites. They have a lot of iron, magnesium, and those particular cactus do very well in areas like that. In regions where there are carbonate rocks, limestones, the spores don't do as well because the nutrients that those cacti like are found in certain rocks, volcanic rocks. So the goals of this course is to give you a basic understanding of earth science and geology. And a basic understanding of geology is a really important process. As it turns out, earth science, any science that deals with studying the earth, it's an earth science. Philosophy, so if you ever take a philosophy class, a lot of the early philosophers, they tried to understand phenomena and how things work. And they were basically embedded into earth science. So philosophy has its foundations, it has its roots in the natural sciences, because the early philosophers tried to understand phenomena, why things work the way they did. For example, why is it that during the winter time of the year in the northern hemisphere, the daylight portion of the day is much shorter as compared to the summertime when the daylight portion is much longer. And they realized that the earth was tilted, that the earth was going through this tilting seasons, and so they really study a lot of natural phenomena. And so we're going to take a look at local geology. There's a lot of neat geology in California. California is unique. It does not belong, with respect to geology, to the rest of the North American continent. We are unique. In fact, California really is kind of a collage of many smaller continents that kind of accreted themselves, stuck themselves onto the North American continent. All right, so geology studies the crust of Earth. So we study rocks and minerals, and these are important. These are essential because everything that we use in our lives comes out of rock. So we have to mine that rock, we have to crush it, take out the essential elements that we need, such as iron and gold and nickel and all those important metals, and then rare earths for computer tablets and smartphones, etc. So this is the source for all resources. Biological operations could not exist if it wasn't for the elements that are found in rocks. So there are 16 essential elements of the 92 elements that are important for life as we know it. And all of those elements are found in rocks. And those rocks that are found on Earth have those essential elements which are essential for life. So geological hazards, we'll look at those. Humans have a huge impact on the Earth. We strip mine our forest. We strip mine the surface for resources, and unfortunately we have a huge impact on Earth. And then there's times when the Earth impacts us through floods, earthquakes, volcanic eruptions, So we'll take a look at a lot of the geological hazards in this course. And then water. We really have to spend some time talking about water resources because water is really an important, of all the commodities out there, it is probably the most essential, and yet it's probably the one that's taken for granted. And especially in the southwestern United States here, in states like California, where populations are growing and we're surrounded by deserts, water's resources are very important. What we try and do as geologists is we try and reconstruct the history of the Earth so we want to understand what happened in the past. So there's a saying in geology that the current is a key to the past. So we see events like rivers cutting down through rock, forming canyons. We assume that those same processes were at work, 400 million years ago. And when we see landscapes that are occurring today, we try to relate to how those rocks were formed. And especially with climate. So right now, the big key to understanding climate is we want to reconstruct all the past climates that we can possibly reconstruct. We have a good climatic record that goes back in pretty good detail about 600,000 years. And that's partially due to ice cores and sediments in the oceans. We're actually able to extract isotopes, and we'll talk about that later on, to reconstruct past climates. And that's going to give us a little bit of an edge when we're trying to predict what future climates might hold. So there's a lot of concern right now about climate. So Southern California has a lot of textbook examples of geology. We're known as the Golden State. We were founded because of gold, basically. We became a state because of the gold rush, the 49ers, 1849. But yet, our neighbor to the east, the state of Nevada, which is known as a silver state, is the largest gold producer right now in the United States and the second largest gold producer in the world. California produces a lot of silver, a lot of other important metals too. So California is a pretty rich state with respect to minerals. And people come from all over to study the geology of California. It's very complex geology. Our rocks are exposed, so you can go out in the desert and drive along and you can actually see the geology. Unlike places in the eastern United States where they're covered up with trees and vegetation, geologists really appreciate the exposures that we have out here. So in contrast to the way humans think, is we like everything to be stable. But yet the Earth is not a static planet. It's a dynamic planet. That means it's constantly changing. And earthquakes, volcanic eruptions, are part of that change. And humans, we have a hard time adjusting to that. So climate is not ever going to be in a continuous state. People like to see it stay the way it has been, and we don't want any change, warmer or cooler. But yet in reality, climate's always changing. It always has changed. It's never been the same. In the past, climate has been much warmer than it is today. Carbon dioxide levels have been much higher than they are today. And there have been times when they've also been lower and the temperatures have been cooler. The big question today, are we in fact having an impact on climate? I definitely think we are, but it's not because of carbon dioxide. I think human anthropogenic climate change is being largely attributed to land use changes. The fact that we're cutting down trees. We're stripping the entire planet of its forest. Places like Indonesia are gone. They have basically stripped all the forests in Indonesia, New Guinea, and places like that. India is having a massive problem with deforestation. People taking teak woods to the point of basically stripping entire regions of that wood. The Indian government outlawed it, and as soon as they outlawed it, the price of teak wood went up, and that encouraged people to actually go out who never would mine the wood, strip mine, and clear cut the land. They're now encouraged to do that because the price incentives allow that to happen. Sea level is constantly changing, both higher and lower. So here are some rocks. This is actually in Utah, right on the Utah-Arizona border. So these rocks are what makes up Monument Valley and Arches National Monument. These are sandstone rocks. They're about 250 million years old. And by understanding these rocks and how they were formed, and once you understand rocks, you can get a really good view of what the Earth was like in the past. So these rocks that are 250 million years old, that's about the middle part of the Mesozoic, the age of the dinosaurs. These rocks were formed in a very arid desert, much like the Sahara Desert is today. So imagine Utah during the mid part of the Mesozoic was a desert, much like the Sahara Desert is today. So those sand dunes that used to cover Utah and Arizona had now been transformed into a rock we call sandstone. This sandstone today is weathering. It's going to go back in the sand again, and that's what nature does. It constantly recycles, regenerates itself, reusing the same elements, same compounds over and over again. These are interesting formations. These are hoodoos. These are actually in Utah. This is a formation that covers a large area of Utah. And when we really look at what's in this sedimentary rock, we discovered that these are rocks that were formed in warm lakes. That is not what the climate in Utah is like today. Utah's pretty cold, lots of snow. And so that tells us that the climate in Utah has changed dramatically. And this is what rocks tell us. One of my favorite places, and a place I got to go right before school started, was Grand Canyon. So here in the Grand Canyon, the very top formation here, this white colored rock is the Kaibab limestone formation. It's about 250 million years old. This formation was formed in an oceanic environment, very shallow, marine, very warm, tropical waters. That's not what the climate is like in Arizona today. It is not tropical. It does not consist of an ocean that's warm. Below that is this red unit. It's red because it has oxidation of iron, iron oxide. And this particular formation was formed completely different environment. It was formed in an area where there were a lot of streams and deltas, moving water, enough oxygen to oxidize the iron, turning it red. And so this would be an older formation. And then this younger formation above it is when the sea encroached over Arizona, flooded Arizona, and deposited this limestone. So the presence of these formations tell us that either the tropics had moved up to Arizona, or at one time North American continent along with Arizona was down south near the tropics. And this kind of is an important thing to understand, that the continents where they are today, they haven't always been in the same place. They're always moving. And this is what Wegener proposed in 1915. So the Grand Canyon, if you look at all the rocks that make up the Grand Canyon, the stratigraphic sequence of rocks, these sedimentary rocks, these were episodes of the oceans flooding the North American continent. Then they regressed, they left the North American continent, they transgressed again and flooded the North American continent. And we can see these sea level fluctuations flooding the North American continent, then leaving, coming in and leaving at least 4 different times. And each time they deposited sequences of sedimentary rocks such as sandstones, shells, and limestones, which are indicative of marine environments. There are fossils throughout the Grand Canyon. And now this formation that was deposited in the ocean was uplifted due to tectonics and then downcut by the Colorado River. So over the past 3 to 5 million years, the Colorado River has been actively carving through these sediments, exposing them. The Colorado River was named Colorado. It's a formal Spanish word meaning red. And the primary color of the Colorado River used to be red because it cuts down to a lot of red sediments. Today it doesn't flow red in a lot of places, especially in the lower part, because we put a series of dams to form lakes, like Lake Havasu, for example, is there because the Parker Dam. And so when they built these dams, they stopped the flow of the Colorado River. They stopped its transportation of red sediments, so the river no longer flows red. This is an interesting concept here. This is a playa. So a playa basically is what's known as a dry lake. So dry lakes, we see them throughout the southwestern United States today. This one is right on the California-Nevada border. And what's interesting about these playas is that if we were here 12,000 years ago, this would have been a lake. There's good examples of fossils. Native Americans inhabited the banks all around here when it was a lake. You find all sorts of Native American remains out here, arrowheads and pottery shards and things like that. And so this is a good example of climate that has started to change about 12,800 years ago, the Earth slowly began to warm, and as it warmed, it dried. So all these lakes that were present 12,000 years ago, when climate was much wetter, cooler than it is today, have since then dried up as climatic conditions turn into more dry and warm conditions. So this is what's neat about geology, is it's like a textbook. It tells us what has occurred in the past. This is actually Death Valley. And the reason Death Valley exists today is because of tectonic faults that are stretching this landscape, dropping these valleys down. Currently, Death Valley is the lowest topographic point in the North American continent, 283 feet below sea level. It's also the hottest part. In fact, in the last week of August, or the third week of August, temperatures in Death Valley reached 130 degrees, which is pretty hot. The reason there are trees here is because there's a fault that goes through Death Valley called the Death Valley Fault. And groundwater from these mountains, when it hits that fault underground, that water emerges as a spring, so you have an oasis out in the middle of the desert. Sand dunes. A lot of sand dunes in Death Valley today. These sand dunes are the result of weathering and then erosion of rock. So the sand grains, the quartz crystals, the quartz sand grains that we find in this sandstone came from a granite that weathered. That material was then transported by a combination of water and wind, and it now exists as a sand dune. We can take this sand dune and compact it and form it into a rock called sandstone. That sandstone can then weather out again. So nature is constantly moving sediments around, just constantly interacting. So sand dunes, there's very large sand dunes out in the desert. This is the Dumont Dunes, which is basically south of Death Valley. A very popular place for people to go sand buggies and sand rails and dirt bikes and all sorts of quads. So why study geology, besides needing a GE class? Well, right now, geology is one of the fastest growing economic sectors in the United States. People who hire for environmental firms, for environmental compliance, remediation, they're really looking for people who have a background in chemistry and geology. It used to be that they were hiring biologists, but right now the trend is for students who have backgrounds in chemistry and geology. So there's a lot of jobs in geology. You can work in the mining industry because we constantly need resources. We need metals and material to build consumer products. Oil and gas industry. Oil basically is derived from rock, along with natural gas. Lab technicians, field work, environmental remediation, and water resources. So a lot of geologists out there studying water right now. There's an entire field of geology, a sub-discipline called hydrology. Water is really important. We're going to talk about water quite a bit because it's an important commodity for the state of California. Mineral resources, soils. So where do soils come from? This is weathered rock. So rock that contains minerals like iron, magnesium, potassium. Those minerals that are in the rocks weather out. And then those key elements such as iron, magnesium, potassium are then trapped in the soils, and those are the really good soils for growing crops. And of course, past climates. We're going to spend a lot of time on climate. So Earth is dynamic. It's a constant state of change, so it's always changing. So the Earth is not a static planet. And this is where humans get into trouble, is that we have this problem where we want everything to remain as it is, static, normal, and it doesn't occur that way. So this is an agricultural field. This is in Coachella. And they're growing lettuce out here, and they're flooding this field. Now when you look at this, you say, well, wait a minute, Coachella is a desert. It doesn't make sense to do this type of agriculture in a desert environment. So why would somebody do that? Why would they waste water? Well, the reason they do is that this water in Coachella and throughout the Imperial Valley and throughout California is subsidized. So farmers pay a discount rate for water. How much? So for 1 acre of land, they will pay $25 per acre per year. A household in Huntington Beach or in Orange County someplace, domestic water using for washing and bathing and watering your outdoor plants, the average household in Orange County will pay $40 a month. $40 a month, these farmers are paying $25 a year. So the water is subsidized, and this is why they're able to grow crops like lettuce in a desert environment and use lots of water, because it is subsidized. So agriculture is a heavily subsidized industry, and when it's subsidized, there is very little incentive to conserve that water. Mining. The one side of geology that's kind of the nasty side is the fact that we have to crush a lot of rock in order to get the resources that we need. So this is actually a mining town called Oatman. It's in Arizona, right across the river, the Colorado River from Laughlin, Nevada. All of this white material out here, these are sediments, the remains of crushed rock that has been crushed and processed. The metals have been extracted. So gold right now, in order to obtain a troy ounce of gold, how much is a troy ounce of gold? Take three quarters together. Those equal about a troy ounce. How much rock do we have to mine and extract to get that troy ounce of gold? About 2 tons in some places. So how much is 2 tons? That's about 4 pickup trucks completely full of rock. So imagine, full-size pickup trucks, 4 of them, full of rock, will get you the same amount of gold as 3 quarters. So we have to extract an awful lot of rock and do an awful lot of stripping of the Earth's surface in order to obtain the resources that we need. So humans impact the Earth through deforestation. This is probably the primary key component in global climate change that's anthropogenic, that's caused by humans. So it's having a huge atmospheric impact. It's also impacting areas such as the Amazon River. The Amazon River is now beginning to flow brown and tan. That's due to the sediment. The Amazon River has never flowed that way. It's always flowed like a green color. The sediment is occurring in the river system because we have stripped the forest, and then when it rains, that soil that used to protect and stabilize that soil is now destabilized, and it flows right off the surface and into the river systems. So resource extraction has a huge environmental concern. We're taking critical habitat areas for a lot of animal species, and we're filling up with urban settings and industrialization. Agriculture, we basically go into an area, we completely remove all the natural vegetation and then put in plants that suit us. I teach a class called Historical Geology, and one of the things we do in Historical Geology, we try and reconstruct the past to understand the current conditions. So that's why we have a whole discipline in geology called Historical Geology. We ignore geology. We build major freeways along fault zones. So if you go out to the interchange of I-15, where I-15, the 10 freeway and the 60 freeways, they're all cut together there within like a couple miles of each other. Those major interchanges were built right across a branch of the San Andreas Fault. Downtown Los Angeles sits on a major tectonic fault, and I'm not talking about the San Andreas Fault. This is actually the Pointy Hills Blind Thrust Fault. The Pointy Hills Blind Thrust Fault starts in Pointy Hills, which is off the 57 freeway near Diamond Bar. It runs across the LA Basin all the way over to Hollywood. So underneath this big city is a thrust fault that they think is more dangerous than the San Andreas Fault. And that has been discovered recently. It was actually discovered by the oil companies, and a couple of geologists from San Diego State have taken the oil company data and studied the fault. And they say that this fault doesn't move as often as the San Andreas Fault, but when it does move, it produces a very near-surface shockwave that can have devastating consequences. So we built these huge 80-story buildings, and they're right in a fault plane. And so sometimes we tend to be a little bit egotistical, and I think we tend to ignore geology an awful lot. So the Earth impacts humans through earthquakes, and you have to realize that earthquakes are part of Earth's processes. As these continents move over millions of years, that movement of those plates generates an energy, a shock wave, known as an earthquake. Right down the Pacific Coast Highway between Warner and the Huntington Beach Pier, there is a fault that runs right along the Pacific Coast Highway called the Newport-Inglewood Fault. Landslides impact humans, floods, volcanic eruptions. A lot of people live right near volcanoes. And you may say, well, why would somebody live near a volcano? Well, as it turns out, volcanic rock has minerals like iron, magnesium, potassium. And when those volcanic rocks weather, they form some of the best soils in the world. So the best soils in the world are right next to volcanoes. And currently, because of human population increasing and the demand for food and the demand for agriculture, we are losing a lot of our soils due to non-sustainable farming practices. So every now and then the Earth reminds us that it's not stable, it's constantly changed. This is actually after the 1994 Northwest quake. This is the Antelope Freeway and the Golden State Freeway interchange. What we learned from that particular seismic event was that these pillars that hold up the bridges, the overpasses, the flybys, these pillars failed. That was an important lesson in the Northwest quake. So as a result, the California legislature mandated that Caltrans retrofit every pillar on every freeway throughout the entire state of California. And the way they're doing that is they're taking very thick steel cable, they're wrapping the pillars, and then they're encasing that in a great big steel plate. So the objective behind all of that is to keep these pillars from collapsing. It's a hypothesis. Will it work? We'll see. Floods. Of all the geological hazards, floods, by far, kill more people on average every year than all other natural disasters combined. So floods, more people die because of floods. And we build in floodplains. There's actually a little place in Vegas, and every time they have a major storm event there, this place floods. Volcanoes. Mount St. Helens erupted. Right now on Earth there are about 50 active volcanoes. They're not active to the point where they're pouring tons of ash into the atmosphere, but they do emit greenhouse gases like carbon dioxide into the atmosphere every day. In fact, the original source for carbon dioxide, which is an essential gas, is volcanoes. So volcanoes produce a lot of essential gases to keep the Earth alive. So we have a lot of local geology in California. We have some really well-exposed rocks in the Mojave Desert. To the south of us, we have the Sonoran Desert. The Sierra Nevada Mountains is a good example of a mountain range that if we did not have the Sierra Nevada Mountains, California would basically be dry. So the Sierra Nevada Mountains is a mountain range that interacts with climate. It allows storms to track along the Sierra Nevada Mountain. Those storms dump a lot of snow in the winter months. That snow then melts and becomes surface water, which is the primary source of water in the state of California right now. And most of that water originates in the Sierra Nevada Mountains. Big Bear is actually part of the Sierra Nevada Mountains, but it's a part that got ripped away by the San Andreas Fault. Palm Springs sits right on the San Andreas Fault, and the reason that water emerged as a spring is primarily because groundwater from the San Jacinto Mountains goes through the valley. When it hit that fault, it comes up along the fault, and that's why Palm Springs was founded. So the San Andreas Fault is really a really important tectonic structure that controls the geology of California. And then we have the Newport-Inglewood Fault Zone in our backyard. We're going to talk about these faults. And then Santa Catalina Island, which is one of the islands of the Channel Islands. Santa Catalina Island is unique. It does not match the geology of the rest of the islands. And in fact, Santa Catalina Island is actually a piece of Australia that broke off. So a lot of the western portions of the North American continent, the Baja Peninsula, all the way up through California, Oregon, Washington, British Columbia, even into Alaska, are kind of what we call accretionary tectonic terrains. These are pieces of microcontinents that stuck themselves on to the North American continent. So rocks teach us about past oceans. They'll tell us about ancient deserts, the evolution of life, past climates, and of course rocks are the key essential source for all of our metals and elements that we use in order to sustain our standard of living. So countries that have a high concentration of metals and resources tend to be wealthy. So the United States is a wealthy country because of our vast amount of resources. Water, really important, probably one of the most important things of all. And yet our water supply in the Colorado River is shrinking. I took this picture of Lake Mead when it was high. You go out there today and you see this big white ring all the way around it called the bathtub ring. And that's because the lake levels are dropping because A, of climatic change and an increase in people, and the demand on water has increased dramatically. So rocks tell us a story. Here's what's neat about rocks. They tell us what type of environmental setting they were formed in. They're almost like books. And they tell us that we should be a little bit more concerned about the planet and the way we treat it. We tend to be egotistical, so this is an example of a river system that is slowly being encroached on by development. So developing is filling in this river floodplain. So when you build your house in a floodplain, guess what's going to happen to it? It's going to flood. And we tend to ignore geology, and then every now and then geology turns around and knocks on our door. So the scientific method is what we should be using. This is what drives science. And so if you want to understand science and you want to have the truth, the whole truth, nothing but the truth, the scientific method is the way to go about that. This is not the method that politicians use. So the scientific method is a step-by-step analysis. It's used in a hypothesis and testing and the theory development. The scientific method is a step-by-step process. The first step is an observation. This is something you either see, smell, or feel, or sense. So one of your senses senses something, an observation. After that observation, we write out the problem. That's the problem statement. So the third step, which is probably the critical step, is the hypothesis. So a hypothesis is an educated guess that requires testing. And then how we test our hypothesis is the fourth step, and that's experiments. So you can do experiments, field work, lab work. And then once those experiments are concluded, we have to evaluate those experiments, and we have to ask ourselves a question. Did the experiment and the results prove or disprove the hypothesis? So let's work through a sample right here. Observation, you come out to your car and it won't start. All right. Is that a problem? Yes, it's a problem because you want your car. You need your car. So now we take our knowledge and what we have stored in our brain and the knowledge, the limited knowledge we have about how a car works. We say, wow, I know I have to have gasoline, it's got gas. It has to have a battery to start, and it's not starting. So maybe it's a battery. So we're going to form a hypothesis. I think the battery is dead in the car. Okay? Bad battery. I'm now going to form an experiment. I can take the battery out, I can test it for amperage or voltage, and let's say I don't have any of those things, so I take it down to AutoZone or O'Reilly or Pep Boys, they'll test it for me. And they put their testers on it. They say, no, your battery's good, it's just not charged. Well, what charges the battery? Well, the alternator. Oh, okay. So you take the battery back, you just disproved your battery hypothesis, right? You rejected it. So you put the battery back, take the alternator out. So we now have a new hypothesis. The new hypothesis is bad alternator. Take the alternator out. Take that down and get it tested. And it shows that it's charging okay. That it has plenty of voltage coming out of it, 14 volts. Okay? Second hypothesis rejected. Go down, put the alternator back in the car. And then we start checking out the electrical system, and we find a loose connection. Tighten up. This might be it, so we tighten it up. Tighten up that loose connection. Run the car. The alternator now starts to charge the battery. So throughout the scientific method, we started with a battery, we rejected that hypothesis. We started with an alternator, second to an alternator, rejected that hypothesis. And then the third thing, we found a loose connection, found that by tightening that connection, that solved the problem. And this is what science does. So when you reject a hypothesis, that's not a bad thing. I know in our society we think rejection is a bad, a negative. You're being rejected, you know. Now, all the rejection does is you take your hypothesis, you go back up and you restate it. And this is how science really works. So after you work through all this, the last step in the scientific method is we have a theory. So we have a theory, and the theory is based on the testing of a hypothesis. And this is what scientists use. So theory comes at the end of the scientific method. It's based on the testing of hypotheses. It's supported by research, by experiments. So theories are based on the testing of a hypothesis. And a hypothesis is not the answer. It simply is an educated guess that requires testing. So we think it's this. How do we know it's that? We have to test it. And this is basically how the scientific method works. So let's put this into something that happened in 1906. So in 1906, a major earthquake hit California. And this was a significant event because this is the first major earthquake to impact an urban setting in California. The city of San Francisco was devastated, destroyed by basically two disasters in one. The first was the earthquake. And then the earthquake resulted in fires that then set the city on fire, which burned for 3 days. So after the aftermath and everything was cleaned up and we started rebuilding San Francisco, a team of scientists were hired in order to investigate why earthquakes occurred or why the San Francisco earthquake occurred. So basically they went out and they started looking at the surrounding area. And this is actually a farm fence. So this fence and this fence used to be one fence. And so they have been offset. They were actually pulled apart by a distance of about 8 feet by a fault. So they saw a crack in the earth here. And they started following that crack. And they found that crack went all throughout San Francisco. And they said, wow, there's a great crack in the earth. And then some geologists said, well, that's called a fault. And they followed it and it ended at a lake. And that lake's name was San Andreas. So they then named the fault the San Andreas Fault. And then over the past 100 years, we've studied the effects of the San Andreas Fault. The San Andreas Fault has been extensively studied. So this is some of the damage that occurred in the 1906 San Francisco quake. Houses that were lined up. So these were all homes that were built out of wood. They were close to one another. So when one house caught on fire, it spread to the next and the next. And that's why San Francisco burned for 3 days. Today we have building codes that say you, from the property line, each house has to be offset by 5 feet on both sides. That gives you 10 feet of off space in between houses. That will help slow down the spread of fire. So the city burned for 3 days because a lot of the structures in San Francisco were made out of wood. That enacted a mistake. So the legislator got together and says, you know what? Because of wood construction that burns, public buildings aren't going to be made out of wood anymore. We're going to make them out of brick because brick will not burn. And so they started building brick buildings. And that worked fine until 1933. The most significant seismic event that ever hit California was the 1933 Long Beach earthquake. The Long Beach earthquake was actually the Newport-Inglewood fault that moved near the border of Huntington Beach and Newport Beach. When that fault moved, it sent a shockwave north to the nearest city at that time, which was Long Beach. All the brick buildings crumbled. And we found out that brick was a terrible building product for earthquakes. So wait a minute. Scientific method said that wood was bad because it burned. So brick won't burn, but brick won't hold to earthquakes. And as it turns out, the wooden houses, they do much better in earthquakes because wood will flex, it'll sway. So this is what science is, a constant ongoing process. City Hall was destroyed. And so the scientific method was used to understand why earthquakes occurred. We discovered the San Andreas Fault. Later in the 1960s, it was discovered the San Andreas Fault was actually a plate boundary between the North American plate and the Pacific plate. And that the fault moves, but not at a uniform rate. So this is a really neat graphic. I like this graphic. This shows the state of California. It shows the San Andreas Fault. And what's neat about this particular graphic is, notice Parkfield. Parkfield has a 90% probability of an earthquake. Down here in the Carrizo Plain, 10% probability of an earthquake. Out in San Bernardino Mountain area, so this is between Coachella and Cajon Pass, there's a 20% probability of an earthquake. So somebody who doesn't know anything about earthquakes, if you told them like, wow, why don't you live in Parkfield? They'd say, no way. There's a 90% chance I'm going to have an earthquake. I don't like earthquakes. I'm going to live in the Carrizo Plain. There's only a 10% chance of an earthquake there. Much better odds, right? Well, this is kind of reversed because Parkfield has earthquakes all the time. But these are very small events, 1.0s, 2.0s. So this portion of the San Andreas Fault is releasing the stress little by little. And the areas such as the San Bernardino Mountains between Coachella and the Cajon Pass, the Carrizo Plain, and up here north of San Francisco, those areas are building a lot of tension. And what geologists, people who study earthquake seismologists, think is going to occur is that when these faults do move, it's going to create a huge 8.0 quake, which will have devastating consequences. So if you have to live on the San Andreas Fault, Parkfield is the better choice than the Carrizo Plain or San Bernardino County. These areas have not had earthquakes, and there's a lot of stored energy. So what we've learned through the scientific method is simply that the San Andreas Fault is this plate boundary between the North America plate and the Pacific plate, and that this fault does not move at a uniform rate. So the San Andreas Fault between Palm Springs and San Bernardino has not moved in 300 years. This section could generate a shock wave easily. An 8.0 earthquake is not even out of the range of this fault at all. It might even go higher. I've read some interesting reports from the Journal of Geophysics. Some of the geophysicists are predicting a 9.0 event that occur, and it's probably something that's going to occur fairly soon. So what does fairly soon mean? 10 years from now, 20 years from now, tomorrow? That's the bad thing about earthquakes. Even though we've been studying them in California over 100 years, we can't pinpoint an exact time for an earthquake. And that is one of the big problems, because you'd be able to like to predict and then take measures to secure the safety of people, but we don't know when they're going to hit. They're the ultimate out-of-control experience. They occur whenever they want, and they last as long as they like, and there's nothing we can do about it. There's no off and on switch to turn off the earthquake. So plate tectonics. Here's another good example of the scientific method, but this is where politics kind of got involved and screwed things up. So believe me, when the politicians get involved, it just goes to muck. So in 1915, a geographer named Alfred Wegener, he had traveled around the world, looked at fossils and rocks and continents, and in 1915 he published a treatise called The Origins of Continents and Oceans. He presented his findings to the Academy of Sciences in 1915, and the basis of his entire treatise was this, that millions of years ago, all the continents that we see today formed one big supercontinent called Pangaea. And that continent then broke apart and the oceans opened up. And he based this hypothesis on 4 major points of evidence. One was that the continents, the modern continents today, can fit together like a puzzle. So you can slide them back together and they slide nicely together. And I have some diagrams that will show that. Second was fossil evidence. Wegener recognized that he found the same identical fossils in 3 different continents. And Wegener said that's impossible. Because if you look at modern biology, you go to Australia, you find koala bears. Koala bears were only in Australia until we invented zoos and moved koala bears into zoos. But prior to that, Koala bears only occurred in Australia. Panda bears, only in China. The Canadian brown bear, only in the Canadian Rockies. So animals were very specific to continents. So Wegener hypothesized that in order to find the same identical species in 3 continents, that biologically, genetically, mathematically, that's impossible. The odds of that are in the trillions. So he said those continents had to be together. So the fossil evidence was the second line of evidence. Then he looked at where coal deposits were. So it turns out coal is formed in a tropical environment. But yet we find coal in Northern Europe. We find it in Pennsylvania, in cold places. So Wegener says when those coal deposits were deposited, those continents were further south, near the equator. So he looked at paleoclimates. And then he looked at the matching geology and he found similarities between Africa and North America. And says that those rocks match, so those continents belong together. And so he uses these lines of evidence and he was rejected. Why? Well, in part, Wegener took everything that conventional scientists of the day thought and he turned it upside down. Back in 1915, scientists thought that the oceans were the oldest features on Earth, that the center of the ocean was the deepest part of the ocean, and that continents were young. Today we know that's not true. Those scientists were wrong. But because Wegener went against the entire scientific community, I can imagine all these guys seem like, who is he to question us? We're professors at Harvard and blah, blah, blah. And so this is where the politics sneaks in. And so because of that, Wegener's hypothesis was rejected. Not because of its content, but I think more of the political. So this is one of his lines of evidence where he's seeing these reptilian creatures, where he could see that they either coexisted, which mathematically and genetically is impossible, or these species lived when the continents were together. So certainly reptilian, early Mesozoic reptilian dinosaurs that lived in South America and Africa, which today are 2 separate continents separated by the Atlantic Ocean, when that species lived, these continents were actually together. And he found that with plants and animals, and the probability of the same plant species being found in South America, Africa, India, Antarctica, and Australia is mathematically in the trillions. It just isn't even possible. You'd have better luck winning the lottery 10 times in a row. I mean, it's just amazing. So the fossils and the rocks, he did extensive studies. He did a lot of research. And so what Wegener proposes is this is what the world looked like 200 million years ago, and that this world then, these continents drift apart. I think the downfall of Wegener is that he cannot explain how this happened. He kind of hypothesized that perhaps there were like icebergs and they floated apart, and he said that was it. That was the nail in the coffin. I'm sure I could hear them just chuckling. But essentially he's right. That is exactly how continents move. They move on plates, and they're moving because of magma underneath the Earth circulating, creating convection, is actually pushing the continents apart. So this is what the Earth looked like 200 million years ago. This is what it looked like 170 million years ago as North America and Africa separate. The Atlantic Ocean starts to open up, and then later South America is going to rift from Africa. The Atlantic Ocean starts to get bigger. North America had a big jump start on South America. It really started going fast. This is what it looked like 50 million years ago. And this is what it looks like today. So today we know, because of submarines, which Wegener did not have a submarine, we know that in the middle of the Atlantic Ocean is a mountain range. It's not the deepest part of the ocean. And this was discovered during World War II with the invention of submarines. Submarines were actually slamming into the mountain. So after World War II, the Navy really wanted to understand what was going on out here. And they went to those scientists, hey, you guys told us that the deepest part of the ocean was in the middle, and guess what? There's a mountain range out there. So they started rethinking about what Wegener had said. And the Navy invested a lot of money into understanding the ocean. They studied the ocean extensively because submarines, they knew, were a future defense. That we could put a nuclear missile on a submarine and hide it anywhere. And if they found out where it was, they could move it. So today, because of the United States Navy, we made some significant studies of the ocean. We discovered a process called paleomagnetism, which we'll talk about in the next chapter, seafloor spreading, and that the Earth consisted of plates. So when Wegener hypothesized that these continents kind of moved across like glaciers, he wasn't really too far off. He just didn't have a way to show how this happened. And when Rear Admiral Hess of the United States Navy discovered this mountain range out in the middle of the Atlantic Ocean and found that new rock was being added, and this new rock was pushing the old rock aside, that basically gave rebirth to Wegener's hypothesis. So in 1915, Wegener called his hypothesis continental drift. Today we call it plate tectonics. So we took Wegener's 4 ideas, and we took, looks like I got a phone call which I'm going to hang up on. Goodbye. I hate phone calls like that. Probably some salesman trying to sell me an air conditioner. It's only 95 degrees now, so that's okay. I can live it. So, Wegener was not that far off. And so today we call his old theory plate tectonics. So we took his 4 ideas, along with 3 ideas that were discovered by the United States Navy, seafloor spreading, paleomagnetism, and plates, combined those into a new theory we call plate tectonics. So today we know that earthquakes and volcanoes are associated with plate boundaries. So along these plate boundaries, this is where you find earthquakes, this is where you find volcanoes. We know along plate boundaries that new crust is being added to the earth and old crust is being subducted. We discovered that the oceans are young, but they're not that old. The oldest ocean crust is about 220 million years old. The oldest rocks found, in contrast to 220 million year ocean, are 3.2 billion years old. So continents by far are older. So everything that those scientists thought in 1915 was upside down compared to what we think today. And Wegener kind of put that forward, and as a result, he was rejected. And I think a lot of it had to do with politics. So if we look at a map of the Earth today, it's along these plate boundaries is where we find earthquakes. Along the plate boundaries is where we see volcanoes. So volcanoes, it's another line of evidence. And this is what's neat about science, is that keep an open mind. If you keep purity and you don't let the politics cloud, which is what politicians do, they screw everything up. I would love to see our Congress revert to the Congress that we used to have back in the George Washington days. Because the early leaders of this country, a lot of them were scientists, like Jefferson and Benjamin Franklin, who wrote the Declaration of Independence. These men were scientists, and they understood phenomena. Today, most of our representatives are lawyers, political science. It's rare to find a scientist or anybody who even understands science. And yet these are the people that are setting forth laws and regulations to look at natural phenomena like climate change and pollution and resources. I mean, come on. These people are not qualified. I mean, especially, you know, when people were losing their jobs and we had the Speaker of the Congress, Nancy Pelosi, show off her 20-gallon ice cream that she buys. Or $20 per gallon of ice cream. I mean, come on, man. We need scientists to really fill Congress and the Senate, and then we can really get to some solving of some real problems. So modern technology, independent scientific investigations 40 years later, with oceanographic studies, the discovery of paleomagnetic studies and magnetism, the locations of volcanoes and earthquakes along plate boundaries, the discovery of plates, all these things basically gave new light to Alfred Wegener's 1915 hypothesis. And this is how science works. Unfortunately, it is often tainted by politics. And we don't really talk about a good political taint when I talk about climate change. Currently, with climate change, in general, if you're a Democrat, you believe that climate change is occurring, and you believe that climate change is a result of human activity. If you're a Republican, you say, no, it's just one of the natural cycles, it's not even happening. In general.
climate change is occurring, and we're going to talk about that. But it's not occurring because of the emissions of carbon gases, CO2, methane. It's occurring because we are cutting down the trees throughout the world. I watched on YouTube when Trump gave his State of the Union address or whatever it was. I watched that. I just watched it just for, just to kind of keep up what's going on. And I'm kind of doing other things, listening to it on YouTube. And I heard something, what? And I had to rewind, go back to the video, and Donald Trump actually said he wanted to actually start replanting trees. So it's like, wow, we have a politician who may actually understand that climate change is being brought about because of global deforestation. I thought that was quite impressive, And I think more politicians need to get on and become more scientific and look at problems not from a political perspective, but look at problems from a scientific perspective. That's how you solve problems. You don't let emotions, you don't let politics mud things up. So when you go through life, try and be fair and impartial and look at the facts and let the facts speak for themselves. I know it's easy for us to be judgmental. I catch myself, I have to stop. I said, no, stop, So this concludes the first chapter. And I'm going to work on getting some better technology. Teaching from our houses is weird. I wish I was back in the classroom where I have much better technology. So this is the low-tech version. Maybe by next week you can see a little bit higher tech version. So maybe we can progress using the scientific method. Have a good week.